Okay, welcome back. Activity 3. Activity 3. Electric field. The electric field outside of a charged sphere. A 10 millimeter radius solid sphere has 10 times 10 to the negative 10th. Okay. Coulombs of charge. Is that just a nanocoulomb? I'm pretty sure it's a nanocoulomb. They could have written 1 nanocoulomb. Alright, the charge is distributed uniformly throughout the sphere. We will go through the explicit steps necessary to use Gauss's law to determine the electric field by this charge at a 15 millimeter distance from the center of the sphere. Okay. The electric field can be determined from the electric flux by using the following equation. True. I like the way I write it better, but yeah, we'll go with this. First, we must see if this equation can be simplified. What is the direction dA, a small part of the Gaussian sphere's surface area? Alright, so for this guy, zoom in, whoop, circle, sphere, outward. So it'll be radially outward. It'll be perpendicular to the surface area pointing outward. That might even actually be the real definition. So radially. Small part of the gas. Okay. Explain why the dot product E dot dA simplifies to E dA for every element on the surface. Well, when we have, I'm just going to use this picture up here, easier. So we have the electric field also radiating radiating from the surface. So all the dAs are going to exactly line up with the electric fields. So here we have, this is going to be cosine of theta, where theta is the angle between the two, dot product, and this will be 1. So E dA equal, E dot dA. And the reason we lose the vectors is because dot products produce scalars. And yeah, that's math. Explain why. Math. You should probably say it a little bit more formally than just math. But I would call math a reasonable answer. Is it possible to simplify the integral by pulling the electric field E outside as shown in the equation below? Yes. Because E is constant at every point of dA. So basically, when you're talking about the surface of the sphere, the electric field at that surface, i.e. that radius, is going to be constant. Because if you look at the electric field equation, you're probably going to have something like kq over r squared. Q, that's not changing. It's, the charge to start with. K, it's a constant, so if it's changing, you've got bigger problems in life. So the only thing that changes for electric field here is going to be the radius. Well, when you say a sphere, you're basically saying a set radius. So what you're saying is, this guy right here is constant. Therefore, E is constant. Bam. Therefore, you can pull it out. So I guess technically you'd have to do this step before you jump to that step, because this E is a vector and this E is a scalar, and the vector E is probably changing along the surface area because it's just changing direction, magnitude and direction. God, what was that movie? That was a great movie. Favorite supervillain ever. So yes, you can. Yes, because E is constant at every point. What? On the surface. What is the integral of dA? The surface area. So the real answer is A. Plus C? I don't know. Basically, they're asking for is the surface area. By means of these two steps, we have simplified the expression for flux as follows. Yes, we have. Why are they explaining this? You've already had to use this like, how many times for the homework that's due in like, I'm pretty sure this lab is done after the last homework was due, in which you already had to use this. Maybe, no, I'm checking this out. No, Google. Physics 1251. Physics 1251 website. Syllabus. Lab 3, electric flux. Yep, and then homework 2 was due right there. Homework 2, you had to do a whole bunch of these. Killing me, Schmalls. All right. This is, I'm not sure why they have these labs. If they're going to test you over a quiz or try and teach you stuff that you already need to know because you're already tested on the homework. Okay, moving on. What two conditions must hold in general in order to be able to simplify the expression for the flux in this way? Well, okay. E must be constant. Yeah, terrible at this. There we go. And theta between E, oh, my handwriting's getting worse, and dA must also be constant. What is the area chosen for our chosen Gaussian surface? We have a sphere, and the surface area of a sphere is 4 pi r squared. Next, we will work on the right side of the equation to determine the amount of charge enclosed in the Gaussian sphere. Okay. Oh, okay. So we have 10. So I'm going to say, so we know that Q enclosed is 10 times 10 to the negative 10th coulombs, which equals 1 nanocoulomb. I think that's 1 nanocoulomb. 1 times 10 to the negative 9th, yes. All right. Insert the electric flux and Q enclosed into Gauss's law and find the electric field. Okay. So let's see, we have flux equals Q enclosed over epsilon naught equals surface integral of E dot dA. So this is going to be E times 4 pi r squared. This will be 1 times 10 to the negative 9th coulombs, or epsilon naught. You know everything here. So therefore, E equals 1 times 10 to the negative 9th times 1 over 4 pi epsilon naught over r squared. I think they said 15 millimeters. 15 millimeters. So it'll be 15 times 10 to the negative 3rd squared. So we have something like 1 times 10 to the negative 9th over, I think that's 225. 15 times 15, maybe, times 10 to the negative 6th times this right here is also known as K, which I just pretty much have memorized at this point. And you probably do too if you've already done your homework. And if you haven't done your homework, then I think it was already due and you just got zeros. All right, 8.99 times 10 to the 9th, that cancels. And we're left with 1 over 225 times 10 to the 6th newtons per coulomb. There we go. Bam, got it. Yep. So the exact process that we've already probably used on the homework about a dozen times, we just learned how to do it. Excellent. All right, see you guys in the next activity.